Imagine closing down a commercial building for the night. The main interior lights must shut off, leaving a single exit door illuminated for exactly 15 seconds. Only after that delay is complete should the exterior parking lot lights activate, and only if a vehicle is actively pulling out. Automating this sequence requires a program that can manage multiple timed delays and conditional triggers without any human intervention. We will build this system from scratch in Siemens TIA Portal. We are using ladder logic, a visual programming language that maps out electrical circuits as digital instructions for the controller. This setup requires 3 distinct networks, one for the system's memory latch, one for the lighting timers, and a final network to process the physical sensor data. Effective PLC programming is about more than just turning a component on. It is about defining the exact conditions that must be met before an output is allowed to activate or shut down. Start by opening the default tag table within the project tree. Before writing any logic, you must define the physical inputs and outputs the controller will use. Hardware uses specific addresses. On the left, I addresses are inputs for buttons and sensors. On the right, Q addresses are outputs, sending commands to lights. Crucially, the car sensor must be an I input, or the program won't detect the car. With the tags assigned, navigate to main OB1 to begin network 1. Insert a normally open contact to represent the physical start button. When this button is pressed, it allows logical current to flow into the rung. Link this contact to a memory coil labeled M0.0. We add a branching latch beneath the start contact, so the system stays active even after the physical button is released. Network 1 now serves as the system's memory, providing a continuous internal signal that the rest of our logic will use as a prerequisite. In Network 2, we will program the shutdown sequence for the interior building lights. Place the Lights Off button condition at the beginning of this rung to act as the master trigger for the shutdown. This schematic compares a standard coil to a negated coil. Negated coils break the circuit when receiving a signal, exactly what we need for the off button. Assign negated coils to lights 1, 2, and 3 using parallel branches, so all rooms respond together. The exit light requires a delayed shutdown. It must stay powered for a fixed duration after the off command so people can leave safely. We use a TP, or pulse timer block. It starts when the in node receives a signal, holding the output high for the duration at the PT node. Enter 15 seconds here. This ensures the exit light stays on for exactly 15 seconds. If the timer is misconfigured or the preset is omitted, the exit light may either fail to turn on or stay on permanently, breaking the automation cycle. While the negated coils provide an instant cutoff for the main rooms, the TP timer creates a precise delay for the exit. This allows the PLC to manage 2 different shutdown behaviors within the same network. Network 3 handles the parking lot lights, which must respond to specific site conditions. Unlike the previous networks, this logic waits for a combination of system states and a signal from a physical sensor. First, we add a normally open contact linked to our M0.0 memory bit to verify the system is active. Next, we add a contact to confirm the Lights Off button has been activated. We then place a normally closed contact tied to the exit light output, ensuring this rung only becomes active after the 15-second exit timer has expired. Finally, we add a normally open contact assigned to the car sensor. As shown in this diagram, these contacts function as an AND gate. Logical current only reaches the parking right coil if the system is on, the building is off, the exit delay is complete, and the sensor detects a vehicle. By integrating the sensor input into this network, the program ensures the parking lights only energize when all environmental and timing prerequisites are satisfied. To test the logic, click Compile, then Load, and start the CPU monitoring to see the logical flow as it happens. Switch to the project view and open Simulation Table 1 to load your project tags into the simulator. Verify the baseline state. Before any inputs are triggered, interior lights 1, 2, and 3 should be in the on state. To start the sequence, toggle the Start button to set the memory latch, then toggle the Lights Off button. The interior lights will shut off immediately, while the exit light timer begins its 15-second countdown. After the timer finishes, test the final condition by toggling the car sensor input on and then off. You should see the parking lot output react to the sensor, turning on when the car is detected and turning off when the sensor clears. This simulation confirms the logic is functioning correctly. These principles of memory latches, negated coils, and conditional timers can be applied to much larger industrial systems. Try adding a delayed off timer to the parking sensor to practice building more complex sequences.